I am an avatar organized by Dr. Alemi to deliver this lecture. In this presentation we will discuss two-way analysis of variance. We use two-way analysis of variance to examine the effects of two completely randomized variables on a common outcome variable. Two-way analysis of variance can also be used to examine the impact of two factorial combination of variables. A full factorial design is the combination of every level of the first factor with all levels of the second factor. The purpose of two-way analysis of variance is to examine the joint impact of two variables. Use one variable to control or block the confounding that occurs among the two variables. Finally, to assess the interaction between the two variables. These data show the length of stay at 3 hospitals for patients with 2 different diagnoses. Notice that the average stay is different at the 3 hospitals, from low of 1.75 days to high of 3.625 days. Notice that the average stay is also different for different diagnoses, from 2.5 days to 2.92 days. In fact, the average stay is different from combination of hospitals and diagnoses. Each cell in the table has a different average length of stay. The purpose of two-way analysis of variance is to see how much of length of stay is due to diagnoses of the patients and how much is a function of which hospital admitted the patient. In two-way analysis of variance there are 3 different null hypotheses. The first one is that all row means are the same. In our example, this is that the 2 diagnoses have the same length of stay. The alternative hypothesis is that at least one of the diagnoses has a different length of stay. The second hypothesis is that all column means are the same. In our example, this hypothesis is that the 3 hospitals have the same length of stay. The alternative hypothesis is that at least one of the hospitals has a different mean. The third hypothesis is that all cell means are the same, i.e. that all combinations of hospitals and diagnoses have the same mean. Interaction occurs when the effects of one independent variable vary based on the levels of the other independent variable. For example, some hospitals are more efficient in certain diagnoses. This shows a typical output for two-way analysis of variance for our data. The first column shows the sum of squares. For rows it measures how much variation is due to the differences between the diagnosis and the average across the diagnosis. For columns, it shows how much the sum of square differs from the average of hospitals. This column shows degrees of freedom. There are 2 diagnoses and therefore the degrees of freedom for rows is 2-1. There are 3 hospitals and therefore the degrees of freedom for columns is 3-1. Mean sum of squares is the sum of squares divided by degrees of freedom. The F statistics is the ratio of mean sum of square divided by within mean sum of square. The critical value from the standardized F distribution is given in this column. The probability of observing the calculated F value is given in the last column. The very high F value allows us to reject that there are no differences among the hospitals. The low F value does not allow us to reject that there are no differences among the diagnoses. The null hypothesis of no interaction effects cannot be rejected. The 3 hospitals differ in efficiency. It is unlikely that these differences are due to the 2 diagnoses. This presentation is focused on two-way analysis of variance and its interpretation. Thank you for looking at this presentation. Please examine other videos we have on one-way ANOVA and use of our software and analysis of variance.